Now let us consider a body on which there is a force acting, which I am denoting by Fi. I hope I am audible. Please raise your hand. Yes, thank you. There is one force acting which I am calling as Fi. You can think of that as the ith force acting on the RB, and that is acting on location I or point I. If that force is known to be conservative, and if Vi represents the potential function of Fi, then we can show that the rate at which work is done by that force on the body, which is this, that will be rate of change of the value of the potential function Vi with respect to time. We will prove it. Okay, we will prove this. I have a figure here. Let's try to understand what I'm trying to explain here. There is a reference frame I, there is a coordinate system shown here. O is a point fixed in I. The same RB, the orientation of the same RB is shown at two different time instants. Same RB. At time t, it is oriented in this way. Time t plus delta t changes its orientation. I mean translation and rotation combined, just moves. It is moving. RB is moving. I focus on this point I, where I is fixed in the RB. At time t, this point I is at location x1, x2, x3 coordinates. At time t plus delta t, the whole RB has moved, and thus this point I has also moved. And now this point I at time t plus delta t occupies this location. There is small increment in x1 and x2 and x3. Small increments are denoted by delta x1, delta x2 and delta x3. If we track the position of I over this time interval delta t using position vectors, then I use RIO at time t and then RIO at t plus delta t. These are the position vectors of the same point on the RB measured from O. And during this time, this conservative force has acted on this particle. So since the force is conservative, it has an associated potential function, and I am saying that the value of the potential function when the particle I is at x1, x2, x3 is this, and this is happening at time t. At time t plus delta t, since the coordinates of the point I have changed, the value of this potential function will also change in accordance with what is written in the argument here. Now what is delta x1, delta x2 and delta x3? That is going to be this. This is delta x1, where v small I big I is the velocity of the ith particle with respect to the inertial reference frame, right? And delta x2 will be this, and delta x3 will be this. Okay. Now if you find if we wish to relate the work done by this conservative force to the change in potential function, I will write delta Vi, which is what? Minus delta Vi, which is Vi at this must be equal to the ith force dotted with delta Ri, delta Rio. Or you can write this as Rio at t plus delta t minus Rio at t. Force is conservative. Now this change in the position vector I can write as this is precisely what this change in the position vector will be. But on the previous slide I said that delta x1 and delta x2 and delta x3 can be related to the local velocity or the velocity of that ith particle on the RB, right? So I am going to replace this taken delta t common outside. Everything had delta t, taken that delta t common outside, and these are dot products between the vectors. Now this expression is nothing but Vi itself. This is Vi. The whole full vector within square brackets, what I have is the full vector Vii. That is equal to minus del Vi. Let us take this delta t on the left hand side. I get Fi dot Vi. Let's set the limit to be 0. What I have is this whole thing. I'm putting a new symbol for this. I'm calling it dvi dt. But the understanding is rate of change in vi as the ith particle on the RB moves with respect to frame I. This is the meaning of this operator, the way I am using, and that equals Fi dot Vi I. This is what I wanted to prove. This is what I wanted to prove here. Okay. Now with this expression, I am ready to simplify the work energy theorem. What is the statement of the work energy theorem? This is what I derived yesterday. I inertial reference frame right? T is the kinetic energy with Ti is the kinetic energy with respect to frame I, and Pi represents the rate at which all forces of the external force system acting on the RB are doing work on the body. Now Pi is Fi dot Vi summation I going from 1 to N. Right? Where N is the total number of forces acting on the RB. And includes all forces, couple, non-couple, all forces included. Now let us say that out of n forces acting on the RB, let m forces be non-conservative. And j forces be conservative. Okay, we have n equals m plus j. We are making two groups, categorizing the forces into two different groups, conservative forces and non-conservative forces. Then I can write this Pi as two different summations. Okay, I would say Fi non-conservative dot Vi I going from 1 to m, and then there is another group I going from 1 to j, conservative. The non-conservative forces I will not be able to simplify any further. But conservative forces I am going to the group, this term, this contribution coming because of the conservative forces I am going to simplify. I'm going to write this as right, based on the derivation I made. For every conservative force F, there will be a potential function V, and thus the rate at which that conservative force is doing work on the RB can be represented as the time rate of change of the corresponding its potential function with time. That's what I am writing here, where Vi is the potential function of the ith conservative force, and these potential functions may be very different functions. So if there are two conservative forces acting on the body, one may be gravitational force, other may be a spring force. The gravitational force will come with its own potential function, which will be something like minus g times x2. The other conservative force, a spring force, will come with its own potential function, which would be kx1 square by 2 kind of function. All those are represented by this Vi. Okay. So with this grouping, the work energy theorem that I have here can be written in this form. The left hand side, which is Pi, I am going to keep only the non-conservative forces, and on the right hand side I already had this rate of change of kinetic energy of the body, and I am going to bring this summation on the right hand side. The minus sign will become plus, right? I can take this time derivative outside of this group and I get inside this simply the summation of all the potential functions, right? And this is the work done. Now let's denote this entire summed up Vj, by one single quantity. I can always do that. Let all these summed up made a mistake here. Don't need J here, should be I. I is the index over which summation is happening. Let us denote this by V, one single symbol. And sometimes we call this as potential energy associated with all conservative forces. Sometimes we call this as the potential energy of the RB itself. We do call it. But whatever you call it, my point is that you sum it up and store all the information in V itself, and then your work energy theorem starts looking like this. Right? Go back here, summed up whole thing I am calling as V. So it is just the rate of change of that V. That is why I am writing it in a more compact manner. And then why don't we just take d dt outside and talk about the sum of kinetic energy and potential energy. The phrase sounds very similar. We have heard this many times. Rate of change of total energy of something is going to be equal to something. Whenever you heard such a sentence, the context is what we have on the board right now. The concept of potential energy doesn't fall from blue sky. It comes into our formulation based on what I have derived so far in this today's class. Starts with the conservative force, then its potential function, then its rate of change, then summed up all potential functions of all conservative forces, and you start calling it the potential energy of the system. So this is work energy theorem simplified. Why do I call it simplified? I call it simplified because now, at least for the conservative forces, I don't have to take this dot product with velocity to get its contribution to the work energy statement or the work energy equation. No dot product with this. You know the potential function, spring force, you know the potential function, gravitational force, you know the potential function. You just add it to the kinetic energy and then take time derivative directly. Less number of dot products. You need to take dot products now only for non-conservative forces. less number of dot products. All right. We do call it total energy. To be very precise, we should call it total mechanical energy of the system. Total mechanical energy of RB. And in the light of this equation, this derivation, if you are enthusiastic about it, you can actually write a new statement for work energy theorem in words. So work energy theorem is telling us rate at which non-conservative forces do work, external non-conservative forces do work on an RB equals rate of change in total mechanical energy of the system. Okay. If non-conservative forces do not do work on the RB, then your total and mechanical energy will not change. Remains a constant. Another simplification. So this looks very attractive because now you don't have to even compute these dot products. You just know that sum of kinetic and potential energy is constant. Indeed, we will use this to solve some problems on Tuesday. Sometimes we talk about the time integrated form of the work energy theorem. Okay, this is the equation I derived. What happens if you integrate it both sides with respect to what? With respect to time. Say t initial, t final. On the left hand side I won't be able to simplify much because I don't know the forces, non-conservative forces yet. So I'll have to keep it like this. Or if I want, I can just write a new symbol for this. Work done from T initial to T final, and I can put a superscript non-conservative forces. That equals that will equal T plus I V final T initial. Now this is an equation I'm sure you have used earlier also many times to solve the problem. And my guess is that as far as problem solving is concerned, you will be able to solve the problems from this course also. However, I would encourage you to pay attention to the details of the derivation. How you get the final expression, which you find very handy in solving problems. What is the concept? What are the concepts that I've undergone, that have gone into that derivation? Pay attention to that. That's an advice from me. Now, when you try to solve a problem using work energy theorem, do draw an FBD. So when you try to solve a mechanics problem using Euler's first or second axiom, of course you have to draw an FBD. That is one of the important steps in solving dynamical problems. I was trying to emphasize this last week, especially in the tutorial class. Step 1, step 2, step 6. FBD is an important part of it. You must draw that. But even for work energy theorem, you should make it a practice to draw the first draw the FBD. Okay. Now, when you draw an FBD before applying the work energy theorem, you may identify some forces which are actually workless forces. Workless forces sounds almost like worthless forces, and indeed they are worthless. Those workless forces are worthless as far as the work energy theorem is concerned. Not only it sounds similar, they act also in a similar manner. Let's have a cylinder rolling without slipping. Without slipping. And this is the surface on which it is rolling without slipping. And at the center somebody is putting a force, say Q vector. Okay. Now if you draw the FBD of it, what forces we will put? We will put here weight, this vector q will be a normal reaction, maybe friction force. Okay. So this is normal reaction, this is the vector force q, force vector q acting on it, this is the center, and then there is mg acting like this, and then there is friction force. Now if I have to find the work done by all the forces, all forces, some of these forces, even though those forces themselves are not zero, their contribution to the work done, or Pi, will be zero. Okay, work done by n will be zero. Why? Because V, let this point of contact be B, B is part of RB, VBI is zero. This is I frame. Sorry, n is not zero. N is not zero, but the n vector dotted with VBI will be zero. N is a workless force. No need to pay attention, no need to pay attention to this. This while using work energy theorem. But if you use Euler's axioms, must include n. This force must be included. Similarly, this friction force, if I represent that friction force by this vector F, that will also be zero. So friction force is also workless force. This is another advantage of using work energy theorem, that some of the forces, they themselves may not be zero, but their work done because of them is zero, and that's why we don't have to worry about them when using the work energy theorem. Okay. In fact, in this case, mg is also workless force. Mg is also a workless force. Why it is workless? Now here Vci is not equal to 0. But if you take the dot product of mg with Vci, that will be 0. That's why it is workless. So Vci will be, of course, horizontal. The work done by force vector q will be non-zero, that you will have to include. But at least we have eliminated 3 forces. Mg is gone, n is gone, F is gone. Alright, keep in mind. And to identify the workless forces, my point was that must draw an FBD. Draw an FBD, include all forces, but then once you are ready to apply the work energy theorem, at that time discount the workless forces. And to be able to identify whether a force is workless or not, you should draw that force correctly at its correct location on the FBD. That much is still required. Okay. Alright, so with this slide, I am done with dynamics. You may recall in the beginning of the course I said there are three parts of the course: kinematics, dynamics, and then statics. First two we are done with. Now it's time to start statics. There isn't much time left for this short summer semester. Nonetheless, I'll try to cover some topics at least from statics. A regular semester also has 42 lecture hours, but somehow during this summer semester I have gone slower than usual, and I do not have adequate lecture time to cover all the topics on statics that I usually cover. I have 2 hours left on Monday and maybe like 10 minutes today. I'll cover the important topics. I'm sure students would not agree with me that I have gone any slow. I am sure many of you are already overwhelmed with the derivations and equations and all. But the truth is, I have gone slower than usual. Anyway, so statics we have defined earlier also, but let's do it one more time quickly to remind ourselves what is meant by this word statics in the context of mechanics. Statics of RBs, of course, is our interest. Statics of RBs, rigid bodies. Study of RB at rest. What do I mean by rest? By rest I mean VCI, velocity of the center of mass of the RB is 0, and omega mi 0 at all times. All times. We also say that the RB is in static equilibrium. Where I is the same inertial frame. Reference frame is still important. An RB which appears to be static or at rest with respect to one frame will appear to be moving with respect to another frame. So frame is still important. And I'm saying that frame also has to be inertial. Then only we say that necessary and sufficient conditions for an RB to be in static equilibrium. Necessary and sufficient conditions. Number 1, at t equals 0, when you started making your observations, at t equals 0, VCI is 0 and omega mi is 0 at t equals 0. And then F net acting on the RB should be 0. And the third condition is moment due to all external forces about any point A of your choice, 0. Any point in space. These three conditions are there, the body will continue to be in static equilibrium at all times. But if the body is already in static equilibrium, what are we worried about? Why do we study? What do we actually want to know? We want to know the relationship between various forces. Of the external force system. That keeps the body in static equilibrium. That's the interest. So if a body is in static equilibrium and there is no external force acting on it, in that case we will never worry about anything. There is nothing to be found. We will leave alone that RB. It is in static equilibrium, no external forces acting, nothing to study there. But there could be some RBs which are in static equilibrium and there are external force systems acting on the RB. We want to study such RBs and we want to know the relationship that must exist between different forces of that non-trivial force system that still keeps the body in static equilibrium. That's the interest. If you count the number of scalar equations, it is the same what we have in the dynamics case. 6 scalar equations coming from 2 and 3. In fact, 2 and 3 are nothing but Euler's first and second axioms. This is actually coming from Euler's first axiom and this is coming from modified Euler's second axiom. So 2 and 3 is nothing new. They are just modified versions of these axioms and these axioms have 6 scalar equations. So you are entitled to get those 6 scalar equations if you take upon yourself the task of doing an analysis of an RB in static equilibrium. Available. Now if you have a 2D scenario, 2D scenario. Okay. External force system is planar. We have talked about such planar force system, right? All forces lying in, say, x1 e1, x2 e2 plane, and torques, if any, parallel to the E3 direction. That's a planar force system. So if you have an RB where the external force system is planar, you have three non-trivial equations relating the forces. F net 0 will give you two right in one direction, in two direction, and the other equation will be MA3 0. This equation, vector equation, will become MA3 third component 0, where A is a point lying in x1 e1 x2 e2 plane. These will become the governing equations. Okay. Now, while dealing with bodies in static equilibrium, we often come across an RB which is under the action of two forces acting at two different points on the RB. We call that RB a two-force body or a two-force member. I'll use this acronym, two-force member, TFM. So consider a body like this, RB. I have one force here, let me call it F1. I have one force here, let me call it F2. Vectors. So a two-force member is an RB is an RB which has exactly two forces acting on it at two different points, and nothing else. Exactly two forces. Such a body is called a two-force body or a two-force member. For example, I have shown a video of a body here, free body diagram. One force is acting at, let's call it A, the other is acting at B. It's a two force member. I'll take 2 more minutes and end the class. Okay. So this body with FA and FB, FE make a two force member. Now the moment I introduce this definition, some of you may think like if I have at A two forces acting like this, FA prime, FB prime, will I call it a two force member? No. Both forces are acting at the same location. At the same point. I said two different points. Then some of you may come up with this scenario that okay, I have FB, I should have put here FA double prime, I meant. It's all about A. I have another scenario at point A, two forces are acting, and then at B, I have another force. Should we call this as a two force member? TFM, yes or no? The answer is no. Not a two force member, not a TFM with FA, FA double prime and FB. Not with these three forces. But the moment you draw the FBD like this, where you have in your mind, in your notes, in your computer program, the moment you have replaced FA prime and FA double prime by a single force, the moment you replace the sum by a single force, it does become a TFM. So this is a two force member. This is not. This is not. So the two force member definition is not only about the net force. It is actually how you draw the FBD. Same force system, if you draw the FBD in a different way, it will not be a two force member. It will not be called a two force member. But then you can alternatively do something like what I did here. Combined the prime and double prime. Put FA at A, FB at B. Let's start calling it as two force member. So the definition is a bit shallow in that way. Shallow means what you see is the way you draw that decides whether it's a two force member or not. That's what I mean by shallow. Now let's look at another case. I have an object and somebody applied FA at A, FB at B, And then C, moment due to a couple, you remember? Is it a two-force member? The answer is no. C has spoiled because of C, because of this, not a two-force member. Again, you may get this feeling of this shallow definition because in your mind the question will come, the argument will come. See, this is FB and this is FA, okay, acting at AB, and this is moment due to a couple. So I can replace this symbol of torque, and instead put a couple of forces like this, such that this makes a couple of forces which has moment this much. And then you will, if you are enthusiastic about your argument, you will say that I will combine this force and write here FB prime, and combine this force and this force, this FB and this couple, the force member of the couple of forces, and I write FA FA prime and FB prime. Now I have two forces acting at two different points, so I have a two-force member. Indeed, this one is a two-force member, but this is not, and this is certainly not. Even though the response of the system will remain the same, response of the RB will remain the same, still TFM is reserved for this situation, not for this, not for this. I stop here. We continue on Monday.